in this module we discuss about logarithmic decrement. Now what is this logarithmic decrement? So this logarithmic decrement is like when a structure is set to vibration, when structure is say vibrating. So if structure is oscillating, because of the presence of damping in the structure, it will come to rest. So what pattern it is following while coming to rest, how much energy is removed in each cycle. So all those things we will study in this module. So we will discuss about response to damped free vibration, logarithmic decrement, and we will solve one example problem, a practical problem we will discuss, like how to find out the damping present in the system by using the principle of this logarithmic decrement. Now response to damped free vibration. So we know in the previous module we have discussed how a response to damped free vibration will be. So it will consist of two parts. One is this part which is exponentially decaying the amplitude of vibration, and then amplitudes are fixed but which is oscillating. This is oscillating part. So this part depends on initial displacement, and this part depends on initial displacement as well as initial velocity along with damping present in the system. So if you look at the amplitude of vibration, which is the square of square root of square of these two terms, sum of square of these two terms A and B. So that is amplitude. Now if we draw the figure of damped free vibration, so it looks like this one. So this part is oscillating part is coming from this bracket term, and the decaying part is coming from this term. And in this we have discussed in the last module also that damped natural period is always greater than or equal to undamped natural period. And now we will discuss about logarithmic decrement. So as you can see, this is the response which is decaying. So this response which is decaying has some peaks here, u1, u2, u3, u4. So we will try to find out what is the relationship between these peaks. So are they following any pattern or not? So that is what we are going to check. So if I take say response, the ratio between the second peak u2 divided by u1, u2 divided by u1. So u2 is occurring at a time t2 and u1 is occurring at a time t1. So the distance between this time gap between this t2 and t1 is td. So like u2 is occurring after one full cycle. So it is something like this. So first peak is u1, and after that the system is moving to mean position and overshooting, and again coming to mean position and again coming back. So the time taken for this peak point up to second peak point is called one period. In this case, because damping is present in the structure, we call it as damped natural period. Similarly, if we look at the time distance between these two peaks is also td. So that means every peak is separated by damped natural period, which is fixed value in this system. So now if we take the ratio of amplitudes, that is u2 by u1, so that means amplitude occurring at time t2 divided by amplitude occurring at time t1. So we can write this t2 as t1 plus td. You can see this one, t2 is t1 plus td, and denominator t1 is ut1. So in this, if we write this ut expression, and in place of t2 we write t1 plus td. This is t1 and t1, time t1. So in this expression we can clearly see that the amplitude, the value of this numerator value and denominator value, these two bracket terms are same. So that means we are left with only this outside bracket, which is the exponential term and exponential term. These two things will remain. So we can write u2 by u1 is exponential minus omega n t1 plus td divided by e to the power of minus zeta omega n t1. So again if we expand this one, because plus symbol is there in bracket. So we can just multiply this 2 and term 1 t1 term will go. So that leaves us with e to the power of minus zeta omega n td. So to remove this negative term in the exponential, we can do this 1 by e to the power of omega n td. And if we reverse it, we can write this as u1 by u2 is equal to e to the power of zeta omega n td. And now we apply say natural log to this u1 by u2 ratio, that will be equal to e to the power of zeta, sorry, e to the power, sorry, that will be equal to zeta omega n td. And as you can see, if we substitute td value, so what is td value? Td is nothing but 2 pi by omega d, and omega d is related to omega n as omega n under root 1 minus zeta square. So if we substitute omega d here and td entire term in this one, we get the natural log of ratio of two successive peaks is 2 pi zeta under root 1 minus zeta square. So this term is called logarithmic decrement. So this delta is equal to ln u1 by u2, log of ln u1 by u2 is logarithmic decrement. So one thing we need to observe in this is this term is independent of time. Independent of time, it is only dependent on damping value. So that means what? The ratio of any two successive peaks is fixed quantity. The ratio of any two successive peaks is a fixed quantity. And another thing what we can notice from this is, for lower levels of damping, if zeta value is low, then 2 pi zeta by under root 1 minus zeta square is approximately equal to 2 pi zeta. So we can directly use as delta is equal to 2 pi zeta. So if we want to find out, we can use delta is equal to 2 pi zeta, where zeta is ratio of percentage critical damping. Now let's solve an example problem using this logarithmic decrement principle. So as you can see here, a water tank is set to vibrate freely. So the amplitude of vibration reduces from 0.5 meters to 0.1 meters in 4 cycles and in 8 seconds. 4 cycles in 8 seconds. Find damped natural period and also find damping. So now if we see this picture, so this is a static equilibrium position, and for setting vibration, so we need to give initial displacement or initial velocity. So in this example, we are giving initial displacement to the system. So 0.5 is the initial displacement to the system, and after 4 cycles the displacement amplitude is coming to 0.1. So that means damping is present in the system. So as you can see this one, so one measure 0.5 meter up to 0.1 meter in 4 cycles. So if I calculate natural period, that is damped natural period, which is 8 seconds 4 cycles, that is 2 seconds. Okay, time taken for one cycle is 2 seconds. So it is taking 2 seconds for one cycle. And we need to find out now damping. So how we can find out damping? So we already know that logarithmic decrement, that is delta is equal to, so delta is equal to 2 pi zeta, delta is equal to 2 pi zeta, but this delta is 2 pi zeta is in one cycle. So we have like from here to here, cycle 1, here to here, cycle 2, here to here, cycle 3, and here to here, cycle 4. So if I write this as say u1, this is u2, u3, u4, u5. So all these amplitudes are there. So what I can do is say u1 by u5 will be equal to u1 by u2 into u2 by u3 into u3 by u4 into u4 by u5. So that's how I get u1 by u5. So what is if I take say ln of here and ln on this side. So what I get is ln of entire thing will be, this will be equal to ln of u1 by u2 plus, as a logarithmic principle, u2 by u3, like that all I will get. So that means each term will become delta. So this is delta, this is delta, this is delta, this is delta. So that will become 4 delta, 4 delta. So that means, so 4 delta is equal to, that means 4 into, so that is equal to 4 into 2 pi zeta, that is equal to ln of u1, that is 0.5 by 0.1. So from this, if we want zeta value, so zeta is equal to, the zeta value can be found out like ln 0.5 by 0.1 divided by 2 pi into 4. So that's what is written here. And value of damping is 0.064. So it essentially means 6.4% damping is present in the system. So in summary, what we have discussed in this module is like how damping is reducing the energy in vibration, and what is the relationship between two successive peaks or any from one peak to another peak, how the vibration amplitude is reducing. So that is what we have discussed.